I think we'll go ahead and get started. Thank you everybody for joining us for our next seminar. I'm Karen Huffman. I'm the marketing manager for Pion, and I also look after our distributors and customers that are located outside of Europe and the US and Canada. So I'd just like to welcome everyone. I'm going to introduce Andrew in a few minutes, but I just wanted to go over a couple logistics. He's going to give his presentation followed by a Q&A, and he's going to be joined by Carl Box, our Chief Scientific Officer for Europe, as well as Haley Watson, who's the Key Account Manager for Northern Europe, and Imogen Knight, who's our Biopharmaceutical Product Specialist. So throughout the presentation, you will be muted, but you can write any questions for the Q&A throughout. You'll see the tabs on the bottom. I think everyone's getting pretty used to a lot of webinars. So if you could just use the Q&A tab to ask your questions versus the chat tab. That way I'm going to get all of the questions written in written format, and we're going to supply answers in a written format to you as well, so that you'll have all of them in addition to ones that we might not have time to answer. You will get a link of the recording a couple days afterwards. It's going to come from Ring Central, but it will include my email. And then your Pion representative will also get in touch with you. Some people's firewalls have blocked links, etc. So we want to make sure that you're able to get the recording, and then also the Q&A questions that I had mentioned. So let me introduce Andrew. He earned his master's in chemistry from the University of Warwick in 2017, and he joined Pion, excuse me, in 2018. So he's been involved with many of you as part of our analytical services team. He's carried out a wide variety of analysis for many pharmaceutical companies across the world. Through his work, he has developed expertise across the entire range of Pion's instruments and applications. But today, as you know, he's going to focus on surface dissolution, and in particular, the SDi2. So with that, I think we're ready, Andrew.
Okay, thank you, Karen. Hello, everybody. My name's Andrew Kennedy, Analytical Services Scientist here at Pion, and I'm based at our lab in Forest Row in the UK. I'd like to welcome you to this webinar on surface dissolution imaging, and I'm going to spend around half an hour or so to introduce you to the Pion SDi2 and what we can learn from the dissolution imaging technique. We start off by asking a question. Why do we study dissolution? Dissolution testing is routinely employed during drug development and quality control for predicting in vivo performance of a drug product, making formulation decisions, and assessing batch-to-batch consistency. Traditional methods such as the USP2 method are well established and well known throughout the industry. These techniques are highly reproducible, compatible with a variety of conditions, and are accepted by regulators to show product performance. However, these methods do have their disadvantages. There is a high burden of both media, up to 1 litre for a single assay, and sample with long experimental timeframes. Quantification of sample must be considered when designing these experiments, and offline sampling is often employed. Sample collection, method development, filtering, and calibration must also all be considered, which can prove expensive and time-consuming for scientists. Sample analysis is usually done far away from the sample, giving only the bulk dissolution story. This may tell you the what of your sample's dissolution, but may not give you answers to the why. Today, I'm going to talk to you about how the Pion SDi2 seeks to act as a supplement to traditional dissolution and uses visible and ultraviolet imaging techniques to address some of these problems and to obtain a greater insight into sample behavior during these dissolution experiments. So, onto the SDi2, which stands for Surface Dissolution Imaging, is a second-generation dissolution imaging instrument developed by Pion, formerly Sirius Analytical, which aims to provide you with a fresh perspective on your dissolution experiments and give new information to help solve your formulation challenges. The instrument has 3 main components: a fluidic system, which pumps media through the instrument and into our second component, one of 2 types of bespoke sample flow cell, and an imaging system employing 2 single wavelength LEDs, which shine through the flow cell and over the sample to be detected by the camera chip. The fluidic system of the SDi2 has capacity for 2 different dissolution media and is able to switch automatically between the 2 during experiments, giving the ability to perform media change assays, simulating the switch between gastric and intestinal environments. There's also the option to run in either open loop or closed loop configuration. Open loop will flow media directly to the waste after passing through the flow cell. Closed loop provides the option to recirculate media back through the system to pass through the flow cell again. Over the next few slides, I will go into a little bit more detail about these components and how they work. I will then discuss the type of data we can obtain and what can be learned from it with a few case studies showcasing the abilities of the SDi2. Ultraviolet absorption is a method routinely employed to monitor drug release during a dissolution experiment, be that in the detector as part of an HPLC system or real-time quantification with an in-situ fiber optic probe. These measurements give us a single concentration point for the bulk solution at a given time point. Collect enough time points and we can build a dissolution curve of concentration versus time. Now, if we collect a number of these absorption readings across a 2D grid of pixels, as shown here, we can then apply a color filter to these values and assign each absorption value with a different color. This gives us an absorption-based image of our sample. Each color represents an absorbance and therefore a concentration value, with red representing high absorbance and blue showing background media where there is no sample present. Scaling up this 100 pixel example to the 4.2 megapixels of the camera chip in the SDi2 gives us a high resolution spatial view of our sample as it dissolves, allowing us to see the processes going on at the surface of the sample along with concentration readings from the bulk. Now, I mentioned previously that the instrument uses 2 single wavelength LEDs in the imaging system, as shown here. This allows us to select one UV wavelength alongside one visible light wavelength to image a sample simultaneously. Combining these measurements in this way allows us to measure the drug release in the UV spectrum, whilst also using a visible wavelength, 520 nanometers, to see through the dissolved material to capture the physical behavior of the sample as it dissolves. The SDi2 has 4 UV wavelengths to choose from: 255, 280, 300, and 320 nanometers to cater for samples which absorb across the UV spectrum. To show what I mean by this, please take a look at these 2 images. These are images collected from the dissolution of a tablet containing carbamazepine. Both images are taken from the same time point of a single assay and show a tablet held in the sample flow cell. The tablets are held in place by a shaped wire sample holder. An example of this is shown in the photo in the middle of the slide. Both the tablet and the wire holder are visible in these collected images. Here, this is the tablet. On the left, we can see the image collected in 300 nanometers in the UV spectrum. We observe a high concentration of carbamazepine close to the surface of the sample and the dissolved drug beginning to diffuse away. In the 520 nanometers on the right, we do not see any of the dissolved material, and as a result, we can observe the outside layer of the tablet is hydrated and swells, giving a less dense area which lets more light through, shown here by the lighter colors around the edge. This hydration and swelling allows the drug to slowly be released to the surface of the tablet and into solution, resulting in a controlled release of drug over time. Now, the SDi2 has 2 types of compatible flow cell to accommodate a wide variety of sample types, such as compacts, tablets, or capsules, across a number of different applications. So firstly, we're going to have a look at the compact flow cell, which is shown on this slide. And the compact flow cell is designed for use with powdered samples. Samples are compacted into a sample cup, as shown in the inset here, and inserted into the bottom of the flow cell. Dissolution media is then flowed through these lines and across the top of the sample surface. This setup allows us to work with very small sample quantities of approximately 5 to 10 milligrams. The defined surface area allows the measurement of intrinsic dissolution rate. The low sample requirement and powder sample addition makes the compact flow cell a powerful tool for early stage compounds. Example applications might include salt form selection, dissolution race testing of test formulations, or excipient screening. The flow-through design and low volume of the flow cell mean assays can be performed over a short time frame, and changeover from one media or sample to another is quick and simple. This helps to speed up decision making and avoids drawn-out dissolution tests or extended cleanup procedures. Our second flow cell, the whole dosage flow cell, is based upon the design of UST type 4 flow-through apparatus. And it's designed for use with formulated whole dosage products such as tablets or capsules. The large 28 by 28 millimeter imaging window and custom sample holders mean that a wide range of sample types can be accommodated within the flow cell. Use cases for the whole dosage cell might include batch-to-batch consistency testing, formulation testing, or tablet coating comparisons. The SDi2 whole dosage flow cell is routinely employed in these applications alongside traditional dissolution experiments as a troubleshooting measure. If you're seeing dissolution results which you did not expect or are unable to explain, the images and videos obtained from the SDi2 may provide the missing piece of the puzzle to unlock the answers to these questions. Now, hopefully, following the introduction, you've gained an understanding of the type of information the SDi2 can provide, and you have an appreciation of how the instrument works. Over the coming slides, I'll be discussing some case studies showing the SDi2 in action and highlighting the capabilities of the instrument, along with what we can learn from the results. So our first example, the effect of dissolved counterions in the dissolution media on the dissolution of a common drug, papaverine, was investigated. A series of experiments were performed, and approximately 5 milligrams of papaverine were added to the sample cup, and solutions of deionized water containing differing amounts of potassium chloride were flowed through the cell. The composition of potassium chloride ranged from 0.1% up to 2.5%. These experiments ran for just 10 minutes, and the media was flowed at 0.2 milliliters per minute. Analysis of the dissolution was performed at 280 nanometers, and the snapshots on the screen were captured following 10 minutes, and immediately show us qualitatively, from the top image to the bottom, that a dissolution of drug is suppressed by the increasing presence of dissolved salt. This is seen by the reduction in size of the sample plume as we move down the screen. So from deionized water, we have a large plume, and then as we increase the concentration of salt, the size of the dissolved sample plume is decreasing. To obtain a deeper look at this, we can probe the dissolution curves obtained during the very same experiments. This chart shows that the mass of drug released from the sample compact over time in each of the media tested. We can now see quite clearly that the dissolution of papaverine is significantly reduced by the presence of potassium chloride in the dissolution medium. What we also discover, though, is that whilst the low amount of potassium chloride seems to have quite a larger impact on the dissolution, we compare the blue deionized water curve with the red 0.1% curve. We observe that the diminishing of this effect as we move towards greater concentrations of dissolved salt. So taking a look at the green 1% and purple 2.5%, the difference between the two is significantly reduced compared to the first two. And this is also reflected in the measured IDR for each dissolution medium. These IDR values are calculated within the SDi2 software package and do not require external calculation. Understanding the effect of dissolved compounds on the dissolution of an active ingredient is important when creating formulations. Using the SDi2 to perform these tests provides a quick and straightforward way to gain an understanding of this type of behavior. All of the data shown on this slide is obtained from a single experiment lasting just 10 minutes and uses only 5 milligrams of sample. Our second example is based around the dissolution of zafirlukast, a drug with extremely low aqueous solubility. The intrinsic solubility has been measured to be less than 1 microgram per milliliter. This makes working with this compound a particular challenge. If you're not able to dissolve the compound to any appreciable concentration, then it becomes very difficult to analyze. Dissolution imaging was used in a simple investigation to analyze the behavior of zafirlukast in various media. Now, zafirlukast is an acid with a pKa at 4.29. So in pH 7 phosphate buffer, the sample will be ionized, and we would expect to see an increase in the solubility. However, we see that the sample still does not dissolve to any great extent. We believe that the sample may be forming an insoluble salt on the surface of the compact. Dissolution of the sample in 1% SDS, or in facid media, shows that the presence of surfactants in the dissolution media doesn't make any significant improvement to the amount of sample dissolved. However, the sample swells up, suggesting that the surfactant is allowing the buffer to penetrate into the sample surface. The lack of any downstream flow of sample suggests that the sample has formed a gel rather than dissolving into the media. A similar experiment was performed to show the effectiveness of solubility enhancing excipients such as Plastone K90. As observed in the image, the drug dissolves into solution, and we see the downstream flow of sample as a tail in the image. These simple experiments were able to quickly show the effect of media and excipients on poorly soluble drugs. The SDi2 is capable of providing useful information even when the amount of drug in solution is very low. Now in our third example, the SDi2 compact flow cell was used to assess differences in the dissolution of diclofenac as a sodium salt and as a free acid. The graph on the left shows the intrinsic dissolution rate measured in 0.01 molar hydrochloric acid over the course of a 40-minute experiment. On the right, the graph shows the cumulative mass release from the same experiments. Runs 1 to 4 show the dissolution of the sodium salt, whereas 1-5, the purple curves, show the dissolution of the free drug. There's very little dissolution observed to the free acid. The IDR remains at 0, and we see little to no drug released over the course of the 40-minute assay. In the case of the sodium salt, we do see dissolution of the sample. However, this dissolution is short-lived. After 10 minutes, the IDR drops to close to 0, and this is reflected in the mass released. At the beginning of the assay, we see sample dissolving from the compact, which reaches a plateau after 10 minutes, and the mass released remains approximately constant. We can turn to the images collected during this assay to help us understand what's going on here. Now, these images were collected from the dissolution of the sodium salt of diclofenac, and were collected using wavelengths of 255 nanometers on the left and 520 nanometers on the right, and were taken at 2 minutes, 6 minutes, and 10 minutes. Inset are photographs of the sample compact at the beginning and at the end of the dissolution experiment. Taking a closer look at the first time point, looking at the sample in the UV spectrum, the sample is dissolving, and we see a sample plume downstream from the compact. This reflects what we see from the dissolution curves on the previous slide. But if we turn our attention to the 520 nanometer image, we start to see a build-up of something on the bottom of the flow cell. Remember that this image is taken in the visible spectrum, and so this is not dissolved material, but instead precipitation of previously dissolved sample. At 6 minutes, we see a continuation of drug dissolving from the sample compact in the UV image, and we also see the precipitated material continue to build up on the bottom of the flow cell. By the time we reach 10 minutes, the UV image shows a much reduced amount of dissolved sample. There is very little sample plume downstream from the compact, and looking at the 520 nanometer image, we can see why. There is a large amount of build-up of precipitated material on top of the sample compact, which prevents the further dissolution of drug. This can also be observed in the photograph of the compact after dissolution. White precipitate can be seen covering the sample holder. Now, the SDi2 is compatible with a Raman probe for simultaneous dissolution imaging and Raman analysis. The Raman probe sits on the top of the instrument shown here, and a quartz window in the top of the compact flow cell allows the analysis of the sample surface during dissolution experiments. Raman analysis was used during the experiments described over the previous few slides to understand what was going on as the sample precipitates and covers the sample compact. As the experiment proceeds, a change in the Raman profile of the sample is observed. This suggests there is a change in sample form taking place. After the initial dissolution of the sample, it converts into a less soluble form and precipitates across the surface of the sample compact, preventing further dissolution. Now, our next case study focuses on the whole dosage flow cell, and in this case, we're going to study 3 marketed formulations of diclofenac. These dissolution profiles were obtained using the SDi2 in a dual-stage experiment. Gastric dissolution media at pH 1.6 was pumped for the first 30 minutes of the experiment, followed by an intestinal sector at pH 6.8 for a further 2 hours. Voltarol Rapid, an instant-release diclofenac product, is represented by the open circles, and we see 2 bursts of release, one immediately as the dissolution is started, and a second burst release on media change to the gastric media. and diclofenac is more soluble under intestinal conditions. The closed circles represent the dissolution of enteric-coated Voltarol tablets, which see no dissolution under gastric conditions, followed by a burst release and a large spike in concentration upon entering the intestinal sector. Finally, the crosses represent Voltarol and retard, an extended release formulation which sees no dissolution during the gastric sector and a slow, sustained release under intestinal conditions. The next slide shows the videos obtained during these dissolution experiments, which display how these different drug release profiles are achieved by the 3 different tablets. Using the SDi2, we can gain an understanding of the mechanism of dissolution, which we do not get from looking at the dissolution curves alone. So on the left, we see the instant release formulation. You can see that the tablet breaks open immediately at the start of the dissolution, exposing the active ingredient to the dissolution media. You see some dissolution and disintegration during the gastric phase, followed by a large release of drug as the media is changed to intestinal environment. In the center, the enteric-coated tablet displays no changes during the first phase of the experiment. Following the change of media, we have a short lag as the coating of the tablet is dissolved, followed by rapid and complete breakdown of the tablet and a burst release of the drug inside. And there's our burst release, dissolving our sample. Finally, over on the right-hand side, the extended release tablet shows a much less dramatic change compared to the other 2 examples. Upon media change, the tablet slowly starts to hydrate and swell as it takes on water. This allows the drug in the tablet to gradually diffuse to the surface of the tablet and to dissolve into the media. We don't see any bursting or disintegration of the tablet, and the drug release is reasonably consistent throughout the duration of the dissolution assay. Now, it's important to point out that although these images are collected in real time as the dissolution experiments carried out, these are sped up videos. So we're seeing our 6-hour experiment sped up to the course of a minute or 2. In all of our samples so far, we've discussed quantitative drug release and dissolution profiles, but all of our observations about the physical behavior of our samples has been qualitative. The SDi2 is capable of quantitatively measuring the dimensions of a tablet in 2 directions, height and width. This allows for straightforward comparison on the physical behavior of samples between batches and formulations. This case study is an investigation into the dissolution behavior of polymer tablets containing carbamazepine. There's an example playing on the slide at the moment of one of these tablets. Hopefully you can see that as the experiment progresses, this tablet is swelling as it dissolves. At the bottom, we can see a snapshot taken at the beginning and the end of the dissolution, which I hope highlights this change. Now, this swelling was measured for 4 different polymer tablets, 2 hydroxypropylcellulose and 2 methyl varieties. Each is a tablet containing no drug, just the polymer alone, at a low drug loading and at a high drug loading. Each dissolution assay consisted of a gastric phase at pH 1.2 for 2 hours, followed by 4 hours under intestinal conditions at pH 6.5. An example of the swelling profiles is shown in this graph. This is the data for one of the HPC polymers. And the tablets containing no drug, shown by the dark red curve here, show the greatest extent of swelling, an increase from approximately 14 millimeters to 17. This is an increase of 3 millimeters. If we compare this to the change measure for the loaded tablets, we see a change of between 1 and 2 millimeters for both the high and the low drug loadings. These are represented by the pink and red curves, respectively. Now, this data was plotted for each of the polymers and drug loadings tested, and a change in height and width was calculated. And these values are displayed in this table here. In each case, we see that the introduction of the active drug to the polymer tablets has an effect on the swelling behavior, and in some cases, significant differences are observed between the swelling of the tablet, dependent on the amount of drug present. As we've seen a few times during this presentation, this type of swelling behavior is involved in a number of extended release formulations. And so understanding how your drug loading will affect the swelling characteristics is crucial when designing these formulations. Now, to finish off, I've attempted to summarize a selection of the applications of the SDi2 and its 2 flow cells, along with a handful of the outputs available from the data. A few examples we've discussed today are salt form selection, monitoring a swelling behavior, or a comparison between tablet materials. However, the SDi2 is a very flexible instrument, so this is by no means an exhaustive list. So in conclusion, the SDi2 gives a new insight into dissolution with high-resolution images of the dissolution processes at the very surface of the sample, opening a window onto the behavior of the samples which is not seen by traditional dissolution techniques. Dissolution imaging allows you to obtain qualitative and quantitative understanding of the mechanisms behind the dissolution of your samples. Two flow cell options allow the instrument to be extremely useful during all stages of drug development journey and able to accommodate a wide variety of sample types. So we've now reached the end of my presentation. I'd like to take this opportunity to thank Kofi Asari-Addo and his group at the University of Huddersfield and Jesper Ostergaard at the University of Copenhagen. They've both been excellent champions of the SDi2, and their work and publications to continue to contribute to the development of the platform, some of which were discussed as case studies during this presentation. Thank you very much for listening and for attending our webinar. We'll now hold a short Q&A session to give you the opportunity to ask any questions you may have. So please submit them using the Q&A feature at the bottom of your screen. Thank you very much.
Thank you, Andrew. Amy, I think you've been collecting some of the questions. If you want to go ahead and start.
Yeah, hi there. Thank you, Andrew. We've got quite a few questions that have just come in, so we'll go through those we'll get through as many of those as we can. The first question we have is, what is the risk of reactivity or equilibrium change when introducing the energy from UV light into the system? And I'm just going to direct that question to Carl.
Yeah, thank you, Amy. So the question was, what is the risk of reactivity or equilibrium change when introducing energy from UV light into the system? Given that we have a flowing system, and a media stream, and this passes through the flow cell in a matter of seconds, unless if we're in an open loop configuration, then I would expect that the reactivity or equilibrium changes or decomposition due to UV light or energy would actually be very low. So we don't foresee any issues with that type of problem. Thank you.
Great, thanks, Carl. And we just have another question, which is, how is data extracted from the images collected? I can send that over to Andy.
Thanks, Amy. Yeah, so during data processing, we set up data collection zones on the images that we collect from the experiments. Now, these are areas of the image that we define for the software to pull data from. For example, we set up a large zone downstream from the sample. From this, the average absorbance is collected and used to calculate the concentration and therefore the sample release from the sample. We also define other zones, such as horizontal or vertical zones across the width of the tablet. And we use this to calculate the sample dimensions. In this case, we set an absorbance threshold. And now above this threshold, any areas of the image which have an absorbance higher than this threshold are considered to be solid sample. And the distance between two sections of the image where the threshold is crossed, this is calculated to be the dimensions of the sample. Additionally, a number of custom zones can be defined by the user, so you can really probe any areas of the sample that you are interested in. And from these zones, an absorbance versus position profile can be extracted. And all of the data from these zones can be exported to Excel for outside manipulation, either as concentration versus time or as absorbance versus position values. You can also export just straight videos of the dissolution profile in both wavelengths.
Great, thank you for that, Andy. We have another question, which is, how long can a formulation be investigated? What's the total runtime that you can run for?
So the SDi2 is capable of